subdomains. So we have one domain which is filled with one material, which we call the solid material, and another domain, subdomain, where it's filled with another material, which we call the void material, typically. And then what we do is we define as an associated design field, which we call gamma. So it's a function of position, and it's equal to 1 in regions where there is solid, and 0 in regions where it's void. Now we want to do optimization, but this does not really allow for gradient-based optimization methods because this is a discrete variable. It's either 1 or 0. So what we do is that we relax gamma so that it is continuous and it's allowed to vary between 0 and 1. And so that means that you might end up with a design field that looks something like this. So it's equal to 1 in some parts of the domain, it's equal to 0 in others. And then there are also other parts where it varies smoothly between 0 and 1, as here. And then what you do afterwards is that you set the material properties to be functions of this design field that you've defined. So, for example, in the context of heat conduction, what you do is that you take the activity and set it to be a function of the design field. So this ends up being the governing equation in the case of steady state heat conduction. Similarly, if you're working with linear elasticity, then you take the stiffness tensor and make it so that it is a function of gamma. So basically, it's kind of like an optimal control problem, but instead of controlling the source term, you're controlling the coefficients in the problem. And so here's what it might look like if you run these topology optimization algorithms. So in this case, we're considering heat conduction, and we have a plate which is heated uniformly across the entire domain, and there is an opening at the bottom where heat can flow out. And so then the optimizer distributes the material in a tree-like structure, which like grasps out at the plate and pulls the heat out into the outlet. This animation shows the optimization process. So it's initialized as uniform, and then you get this tree structure afterwards. So what you end up with in the end is high contrast in the coefficients, very typically, and also designs which contain quite small details like these small branches. The name topology optimization comes from the fact that it has the option to change the topology of the design, which is something that many other design optimization algorithms don't have. And this is especially visible in the domain of structural design, where you often end up with these designs which contain many, many holes. Topology optimization has numerous applications. It can be applied to anything involving heat transfer, solid mechanics, fluid mechanics, electromagnetism. And I'm working with topology optimization of transient problems, and this is expensive because you need to do several simulations of the design that you want to optimize. In addition to that, you also need to do an adjoint simulation, as was also mentioned yesterday for optimization problems. And the processing time is proportional to the number of time steps, at least if you use sequential time steppers. And so you already know which conference we're at, so you already know what the solution is going to be. It is parallel time methods. For the time being, we're considering transient heat conduction as a model problem, but we want to move on to more complicated stuff later. We've tried to apply parallel to this, for that we learned that it's important to remember to store all the time steps that are evaluated by the fine propagator when you execute it, because you need all of those time steps for the adjoint analysis. And we also learned that it is a very good idea to use warm restarts because that allows you to get speed ups that are less bad than they would be otherwise. We also learned that it is pretty easy to work with, which is nice. However, it suffers from poor scalability, at least in our case. That's what we see here. So this is the speed up factor as the function of the number of processors, and we get a speed of around 5 for around 60 processors.
It's pretty good.
Well,
It's pretty good.
Well, yeah, because we use warm restarts, and that's where it comes from. But anyways, it kind of drops off as you add more threads, and that's due to the cost of the coarse propagators. It becomes more and more expensive as you add more threads. So we're not quite satisfied with the result, so we have moved on to something more potent, which is space-time multigrid. Now, these were also introduced yesterday, but anyways, just to recap, these are derived from normal multigrid methods where you have a hierarchy of grids, and then you use smoothers and coarse grid corrections in order to solve the problem in hopefully over time. Space-time multigrid methods are then applied to space-time domains. So for example, you might have a domain which contains one axis of time and one axis of space, as illustrated here. One thing that you always have to worry about with regards to these space-time multigrid methods is anisotropy, because space-time domains are inherently anisotropic because the dimension of time is different from the dimensions of space. One of the consequences of that is that if you use pointwise smoothers and combine them with full coarsening of your grids, then this often leads to quite poor convergence rates. And there are a few solutions for this. So first of all, you can use semi-coarsening, where you basically, and this was proposed by Horton and others, where you basically can decide either to use only bigger spatial steps or only bigger time steps on your coarse grids, or you can choose to use full coarsening where you do both. You could also use more advanced smoothers to get around this, which is something that was explored by Franco and others. Or you could use a mix of both of the above, which is something that Martin and others have been exploring. In our case, we have decided to go for the semi-coarsening approach exclusively, because we thought this would be easier to implement in parallel, because pointwise smoothers are easy to implement. Now, when you do this semi-coarsening, it's not irrelevant which direction you choose to coarsen in. So in particular, you should coarsen in the direction of strongest coupling of your discretization. So in the context of diffusion problems, that is determined by this parameter, which we call lambda, and it is equal to the diffusivity times the time step divided by the spatial step squared. Now, this parameter has several names, but I choose to call it the anisotropy parameter. And here you can see how this parameter dictates the optimal coarsening rule. So if you have large values of lambda, then it is optimal to use spatial coarsening. If you have small values of lambda, then it's optimal to use temporal coarsening. And meanwhile, full coarsening is always suboptimal, at least for these pointwise smoothers. So that leads to this very simple coarsening strategy, where if lambda is smaller than a threshold, then we do time coarsening, otherwise we do space coarsening. And we apply this to every grid in our hierarchy, as proposed by Horton and others. So this is quite simple. However, it's mainly meaningful in the context of uniform domains, because However, we are of course working with high contrast problems. So in realistic heat conduction problems, the contrast in simply be on a factor of around 1,000. And you may recall that lambda is proportional to the diffusivity. So that means that you can easily have situations where lambda is large in some parts of the domain, while it is small in other parts of the domain. And so then the question is, what do you do then? Now, there are a few possible solutions for this. It might be possible to use non-uniform space-time meshes, so where you basically coarsen in time in some parts and coarsen in space in other parts. You could probably also use algebraic multigrids, which was also mentioned yesterday, because it automatically detects the direction of strongest coupling locally. However, we have decided to investigate using only geometric multigrid methods along with uniform spacetime meshes. And in that context, we have found this effective anisotropy parameter. So it is the geometric mean of the minimum and maximum value of lambda. And it seems to us like this is a pretty reliable indicator for which coarsening direction you should choose based on a bunch of numerical experiments that we have conducted. Now, this was something that we found by trial and error, basically. So we also tested 7 other expressions for how you could define this effective anisotropy parameter, and none of those were as reliable as this. However, I have reason to believe that this is not universal, so it probably depends on the type of smoother that you're using, because I found another paper which encountered a similar problem, but they, instead of using this, they just used the minimum value of lambda, and for them that seemed to work fine. So yeah, this is probably not universal, but it works quite well for our purposes. Yeah, so anyways, the reason why we want to use spacetime multigrids is, of course, because we want to speed up. And in the abstract for this talk, I wrote that we can achieve a 10 times speed up for 6 times the core hours. And this result is now outdated. So this was an experiment we did at the time where we didn't know that semi-coarsening was beneficial. So now that we have implemented semi-coarsening, we can get like 20 to 50 times speed up, or 5 to 10 times the core hours. And this, I should say, is relative to time stepping using spatial multigrid method at each time step. Yeah, so that's pretty cool. Anyways, we've done some topology optimization with that. So here I'm showing 2 examples. So one where the diffusivity was allowed to be very high, and one where it was not so high. So in this example, we get what we basically saw earlier, where it wants to build a tree that conducts heat down into the outlet. However, if you lower the diffusivity, then the heat basically doesn't have enough time to be conducted down into the outlet, and so then it basically just builds a lot of structures with high heat capacity and tries to conduct heat into those little patches. Yeah, and so for this we used flexible GMRS with spacetime multigrid as a preconditioner to do our simulations, both the forward and the joint. And we used a spacetime mesh with these dimensions. So that gives us about 500 million elements, and also around 500 million DOFs. Yes, they're called DOFs. Yeah, so, and this was run on about 5,000 cores. And in the case with high diffusivity, we were able to do this topology optimization in 49 minutes. And in the case with low diffusivity, we were able to do it in 69 minutes, which is nice. So my supervisor has also been toying around with time-dependent designs. So where we don't say that the design field is a function of space only, it's also allowed to be a function of time. So we get these time varying designs where in this case, this is the direction of time and the other two dimensions are the directions of space. And so for that, we use a space-time mesh with these dimensions. So that gives us 4.2 billion elements. And I'm told that this is a new record for the most elements in a topology optimization problem. The previous record holder was like 1 billion elements, if I'm not mistaken. And so this is also around 4 billion dots. And this was run on around 25,000 cores. And for this, we were able to do topology optimization in around 52 minutes. So that's pretty cool. And here we see an animation of the design. So now we see these are the two spatial directions, and time is just animated. And so in this case, this is a moving heat source that goes around in a circle, and then the design basically conforms around this heat source and tries to conduct the heat out through the walls. Yeah. So anyways, for future work, we attempted to try work with nonlinear heat conduction. So for example, in the context of phase change materials, where you have basically, in our case, our intention is to just use the heat equation, but then we put in the latent heat of the material as a kind of really high heat capacity locally at the point where the phase changes. So that means that you have this like moving interface between the phases where the heat capacity is basically very, very large locally. We also want to look at transient fluid flow. So in particular, my supervisor has been struggling for a long time to do topology optimization of these devices called fluidic oscillators, where you have an inlet where you pump in a fluid, and then it goes through this chamber, and then out of the output you get this oscillating jet, despite the fact that the device itself does not have any internal moving parts. So that would be nice to do that, and one of the main bottlenecks in this process is the simulation time. It takes a long time to simulate this. So yeah, that will be interesting. And also, speaking of my future work, I would like to make an advertisement. So I am looking to do a stay abroad. So yeah, so I'm thinking about like 3 to 6 months. And it can be about basically anything that that was mentioned in this presentation. So it could be optimization problems, adaptive spacetime meshes, spacetime multigrid, algebraic multigrid, or other hint methods. So yeah, if you would like to invite a young and handsome to collaborate with you, then do get in contact. My email address is here. Yeah, thank you for your attention.